Great. So we're going to take our foot off the pedal a little bit and review what we've covered and have a few discussions that don't cover new material but reinforce the old material. So let me write down the definition of the covariant derivative. So the way you define these operators in this notation is by giving an indication of what you do for every type of index. And this rule is that you take a partial derivative, which of course does not produce a tensor, t, c, k. And then each index gets its own term with the Christoffel symbol. Contravariant gets a plus, I, k, m, t, m, j. And I once again want to say you don't need to memorize this definition because the indices pretty much place themselves. K goes down because we're taking the derivative with respect to zk, then it steals j, and the new one goes on top. That's the only place it can go now. T, I stays put, and j gets replaced with m. So this is not a one rule fit all. This is just an indication for what you do for every type of index. So the immediate conclusion from this, which echoes the discussion we just had, is that if you apply this definition to a variant of order 0, or more interestingly an invariant, it becomes just a partial derivative. Since there are no indices, no extra Christoffel terms for that operator. So you just look at everything as a recipe for what you would do. It's not a final formula. It's just an encoded recipe for applying this derivative. So this derivative applied to an invariant, and this invariant could be a scalar, in the sense a number, or a vector, such as the position vector. It's just the partial derivative. And you can say that that's property number 1. That for invariants, or variants of any variant of order 0, the covariant derivative is simply the partial derivative. That's property number 1. It's kind of quote-unquote obvious, but it needs to be stated explicitly.
Yeah, why wouldn't that be 0?
It's not 0. I'm sorry. The result of this is not 0. It's just that there are no additional terms. There are no additional terms because the way this definition reads is for every, did I say it was 0?
No.
Oh, okay. Is that for every index you get a term that includes the Christoffel symbol. And because this t has no indices, we have the partial term just like here. That's the common part of the definition. And then because there are no additional indices, there are no other terms. So when you apply the covariant derivative to a variant of order 0, it's just the partial derivative. That's the only statement. And then it can be whatever you want. So we can, for instance, write that the covariant basis, it's often very useful to write this, is the covariant derivative of the position vector. You no longer have to write partial derivative, because partial and covariant are the same thing when applied to an invariant. That's property number 1. Property number 2, I'm not even going to write down. Should I write it down? It would be confusing if I wrote out the whole thing. I'll start the sentence and you'll finish the sentence. In Cartesian coordinates, covariant derivative coincides with partial derivative, because the Christoffels vanish. What's the most general type of coordinate system where the covariant derivative is equivalent to the partial derivative?
Affine.
Affine. That's right. As long as Christoffel symbols vanish, in other words, the covariant basis is unchanged from one point to another. That's only true in affine coordinate systems. You can take that as the definition of the covariant coordinate system. Then the covariant derivative coincides with partial. That's good. So this is my diagram. This is my affine coordinate system. I think I've broken the streak of awesome drawings, but that's not bad. Here is a very subtle property, but extremely important. And it's good practice let's look at symbol like this. Let's see, should I erase? No, we'll just operate in this area. If I apply the covariant derivative to a tensor, let's say, should we do order 2 or order 3? We'll do order 3. Let me think about it. Yeah, let's do order 3. But it's contracted. Ij. Consider this expression. And realize that you can interpret it in 2 different ways. Way number 1, you consider this variant. Again, I could just as easily be saying tensor. But this derivative applies to variance and has all of the same properties with respect to variance as it does with respect to the special variants that are tensors. So I might say variant, tensor interchangeably in this context. So if you look at this variant, it's a variant of order 3, to which you can apply the covariant derivative in the sense of this definition, and you'll have 3 additional terms. And you'll end up with a variant of order 4. And then within that variant, you'll contract the 2 corresponding indices. That's one interpretation of this expression. Take the covariant derivative first, do the contraction second. The second interpretation is take this variant of order 3, do the contraction. Now you have the variant of order 1. And apply the covariant derivative to the variant of order 1 in the sense of this definition, where there will be only one additional term. Would those 2 things be equivalent? Well, let's actually erase the board and just try it cleanly. We'll do it first in one sense, then in the other, and then we'll see if the 2 results are the same, and then we'll check in on the score. I'll keep that. That looks very nice, doesn't it? One of the straighter equations I've written all quarter. All right. Here we're going to do approach A. We're going to do the covariant derivative first. So that means that you have to look at it in this sense. Delta T I M, well, better say M for something else, K L N. That's a better letter. O, because it's going to go away. O J, great choice. Equals, well, you have no choice but to write out the definition. We might not even have to do it the other way. So why don't you guys do it on your own and then look up and see if you did it correctly. So interpret this definition for this kind of object and then look up and compare. Okay. Who's doing it on their own without looking up first? Okay, good. Yes.
What's the last one with a G on the end?
Oh my god, I messed up. Get it? Oh my god, I messed up. This will be edited out. In tensor calculus and in all of math, you have to have made every mistake you can possibly make, and then you learn something.
So do you think of it as just subtracting the lower indices when you expand out? So if you had an ij on top, or an ik, or
No, but I don't think of subtracting them out, it's just that I know when I'm operating, I think of it as operating on indices. And I just remember that when I operate on a lower index, I have to use the minus sign and then a different arrangement of the Christoffel symbol. Yeah.
Yeah, for the lower two symbols on the Christoffel symbols, how do you place those again? I understand like with the M when it's contracted with the T soup now.
So when I'm writing this term, I know that I'm operating on the O.
Yeah.
And so, and O is on the bottom here, so it will go into the bottom of the Christoffel symbol.
Okay.
And K is always on the bottom of the Christoffel symbol.
Okay.
So I write down capital G, and then I write KO, and then the one remaining space is the upper index, so I put M there.
Okay.
And then I write this, and instead of O, I write M. It's really the only way, it's really the only way it writes itself. As I was describing it, I'm realizing it sounds complicated, like there are many steps. But when you're actually doing it, there's really no choice. So here I knew I was operating on J, so K on the bottom, J on the bottom, it steals J, then M on top, and then J is replaced by M.
What dictates the order in like
Here?
no, like in the like the TIOM? Why is it not MO? Or does that not matter?
Oh, no, it matters very much. But it was OJ, and when I was operating on O was replaced by M, and it became MJ. And in the second, and then J was operated on,
Oh,
so
okay.
J was replaced by M. So really, it's as if there are no, when you're operating on any particular index, it's as if the other two
Replace it
indices
with
are
an
not
M or
there,
something.
they're just
Okay.
unchanged. So here I and J, here I and O, and here, where am I? K and, what am I saying? And here O and J.
Okay.
Yeah,
The lower indexes and the Christoffel symbols are symmetric though.
that's right, so it doesn't matter.
Okay.
Yes. Have we proven that yet?
I think we did it in that like meetup yesterday.
We did.
Yeah.
No, we didn't prove it. You
No,
just
we
said
didn't.
it. Yeah,
But
we
I
said we
keep
proved
mentioning it. So we're gonna do it in the next segment.
Yeah, you were there. Is that 2 days ago?
Yeah.
You were there, yeah. Oh, that's right. But you were at the tail end of your tequila. So you know what I mean. Okay. Yes? Okay, so this is, get back to the problem we were doing. This is doing the covariant derivative first, and then doing the contraction. So contraction means O gets replaced with I. So I'm just going to go through the whole expression and replace O with I. O, 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 O.
And you can just do that. You don't have to do.
Well, why not? If I have a system of order 4 here on the left-hand side, and a system of order 4 on the right-hand side, or something with 4 like indices, couldn't, and they're the same, they're equal, couldn't I just do a summation on both sides? If two sets, so this is 3 to the 4th, 81 numbers here, 81 numbers here, and then they're the same 81 numbers, and then here I pick them out in a particular way and do a summation, and on the right hand side I'm picking them out in the exact same way and doing the exact same summation. So yes.
But you don't have to go through and multiply by like a delta and.
No, contraction. So I realize that caused this confusion where you think of contraction as multiplying by something else. It's not multiplied. So actually, when SI gets multiplied by TJ or TI, it's opposite order. So when you see this, you think of this as a contraction. And whenever you contract, you think that you have to contract two things together. That's not what contraction is. So the way I think about it is first what's called, I hate giving it a term because it's too simple to have a term associated with it, but this is called tensor product. The result of this is a system of order 2, like a matrix. We can call it Uij. That's step number 1. Once you've performed that step, then comes step number 2, contraction. Contraction is when you have a system of order 2, and then you quote-unquote find its trace. That's contraction. So contraction is actually something that happens on a single object, not when you bring two objects together. So when you see contraction SITJ, SITI, think of it as two operations. The first one is when you find the tensor product, and that results in a system of higher order. And then once you have that single system, you do contraction on it. So contraction is not taking two objects and making it one. Contraction is taking two indices and making them go away. You're contracting the dimension of the object, dimensions of the object. So that's what I'm doing here. TI, so it was a system of order I. Where am I? I. That's it, right?
In the beginning,
I'm sorry?
the very beginning,
I. Okay, so here we have an interpretation where the derivative was applied first, and because we had 3 live indices, we ended up with 3x. I went for the wrong one. That's why. Sorry. This one. T. I was wondering where my empty slots went. There. What have I done to my straightest expression of the quarter? Okay, so the interpretation that we see here is apply the definition first, and because there were 3 indices, we ended up with 3 Christoffel terms, and then take the result, a system of order 4, and perform the appropriate contraction, end up with a system of order 2. If you notice, there are 2 live indices, J and K. Just like on the left-hand side, there are 2 live indices, J and K. And the rest are contracted away. Now, can you see 2 terms here that potentially cancel each other? So, of course, if anything, it would be the 2 terms corresponding to these 2 indices. So we're thinking about this term and this term. And let me know if you think that they're equal. They're not equal literally. As combinations of characters, they're different. But do they represent the same system of order 2? Yes. How do you see that? What indicial manipulation do you need to perform to see that they're the same?
Rename I and I.
That's right. Rename M into I and I into M, and then the 2 terms are clearly the same. And of course we can do that because the summation that's represented, or the summations that are represented, are exactly the same. So these 2 terms go away. We're left with this and this. Okay, that's interpretation number 1. Let's do interpretation number 2, which is contraction first. Here, we right away apply contraction to something like this. I do not want to introduce a new letter and call this Sj. But if you have any difficulty applying this definition, just think of this as Sj. I is not here anymore. It's just a new system called Sj, and it becomes d t I j d z k, and then one Christoffel symbol, minus, and let's work on this Christoffel symbol together. K goes on the bottom, J goes on the bottom, then M has no choice but to go on top, gamma, K goes on the bottom, J goes on the bottom, M goes on top, and replaces the J in this symbol. And is it the same thing as we saw before? Yes.
But you could expand that out with the other two Christoffel symbols.
I could not. I could if my interpretation was different. If I kept thinking derivative first, contraction second, right? Each one of these terms is still ambiguous. Even in this term, do you do the derivative first and then the contraction? They obviously commute, because contraction means addition, and derivative means derivative, and derivative and addition commute. But here as well. Well, actually, in this term. But our interpretation was contraction first, therefore contraction has already been done. So we have a new system that's just called Sj. If we stick with that interpretation, there is nothing else to do, because it's just a system of order 1. And there you have it. The covariant derivative commutes with contraction. Therefore, symbols like this are not ambiguous, or worse yet, contradictory. Because you can interpret it either way, and the result is the same. So that's, what number is this? This was property number 3. Property number 4. We've mentioned, I'll just mention it just so that we have a complete list. Number 4, the metronylic property. The metronylic property states that the covariant derivative applied to the covariant basis, to the contravariant basis, to the metric tensor, to the contravariant metric tensor, and finally, what object am I missing from this group? Kronecker delta, because it's just a metric tensor with an index radius, as well as Kronecker delta, all equals 0. Yes?
When you take the covariant derivative of a metric tensor, doesn't that kind of conflict the index juggling thing? No?
Let's see. Here, so if I just look at this object,
Oh, but there are no dots.
yeah.
Okay.
Well, I know what you're talking about. Here is what you mean. If I had an identity such as this, if I had an identity such as this, S-I-K equals delta K, not delta, covariant derivative sub K of Ti. Suppose I have this identity, maybe it's a definition. Can I conclude from that, as this also holds, that if I were to lower the index on the result, it's the same as lowering the index on Ti first, and then applying the new covariant derivative to it? So from this, does this follow?
Yes.
Yes, and it's very subtle. It's super subtle, because what you're going to do is multiply both sides by Zij, and Zij here as well. And then because of the combination of the product rule and the metronylic property, you can bring this covariant metric tensor inside the covariant derivative. It's only because of the metronymic property. If this wasn't the case, then multiplying this out by the product rule, you can see there would be an additional term. And then, so this becomes j on the bottom, this becomes j on the bottom, and so you obtain this expression. So I think that's what you were thinking
So
about.
it's like a constant. When you
It's
take
like a
the-
constant, that's right. With respect to taking derivative, it's like a constant, which is what it's like in Cartesian coordinates. So all of these things, when it comes to being a term in a product which is being differentiated, they act like constants, which is the same as they would have been in Cartesian coordinates. In Cartesian coordinates, when you apply the derivative to something and there is the little I vector, you treat it as a constant. And in curvilinear coordinates, you couldn't have done it with a partial derivative because it's not a constant. You have to worry about differentiating this, but not this. So it's kind of all of the simplicity of Cartesian coordinates is restored by switching from the partial derivative to the covariant derivative. The simplicity is restored and the generality is retained. So we've retained the generality of curvilinear coordinates without giving up the simplicity of Cartesian coordinates. It's kind of, I can't imagine anything better. It's the best of both worlds. You could not have done this, by the way, if this was a partial derivative. Without, right, these two would have been inconsistent. You cannot go from what I have now on top to what I have now on the bottom. Because with a partial derivative, it matters very much whether you take the partial derivative first and then lower the index, because that means take the partial derivative and then contract with the metric tensor, or do it in the opposite order, contract it with the metric tensor first and then take the derivative, because the derivative of the metric tensor doesn't vanish. We have an expression for it in terms of the Christoffel symbols. Okay, so property number 5 would be the product rule, also known as Leibniz law. All right, I'm not sure if I'm missing one more, but here is a super critical one. Here is a very interesting question. And a preview of curvature. A short preview of curvature. If I have a tensor, so now actually I will refer to it as TK. Doesn't have to be a tensor, maybe just a variant. And I apply to it two covariant derivatives in succession. So you guys see what's involved here? What's involved here is if I were to just write out the definition for this, it would be one partial derivative and one Christoffel term. But then when I apply this to it next, it will be a partial derivative of that whole mess minus two Christoffel terms.
Why two?
Because now we have a system of one or two. So J will get its Christoffel symbol and K will get its Christoffel symbol. So the result will definitely have a double partial derivative of this. And it will also have actually a partial derivative of Christoffels, right? Because this has a single Christoffel. So this will have a partial derivative of that Christoffel symbol. And a single partial derivative of this. Tricky. So this is actually, if I were to write down its definition in terms of partial derivatives and Christoffel symbols, it would be huge. Okay? And then if we did it in the opposite order, excuse me, K, I, T, K. would I get the same thing? Do they commute? So we know that partial derivatives commute, but do covariant derivatives commute? It's a phenomenally simple question and a phenomenally profound question. So we're actually going to answer this question right now. So now let's think of, to use the argument that we're about to use, let's think of TK as a tensor. Let's take a vote. Who thinks they commute? Who thinks they don't?
I think they're very close though.
Yeah.
Who thinks that they commute but has a little bit of doubt? All right. So let's think about this difference. And let's think about this difference. So actually, over here, I will write out a funny expression, not a funny, an extraordinarily beautiful expression for what this difference is. Let's think about the sort of mess that's in here. So this will be one partial derivative and one Christoffel symbol that multiplies this tensor again. And when you apply this symbol to it, you'll get a partial derivative of that. So we'll have a second derivative of the tensor itself, combined with the first derivative of the Christoffel symbol, and another first derivative of this tensor, minus two Christoffel terms, and each one of them will have two Christoffel symbols in it. Because there's already a Christoffel symbol in this part, and this will get multiplied by another Christoffel symbol. And then the same thing will happen here. And then fortunately, there will be some cancellations because of symmetries. For example, the second order partial derivatives of this will go away, right? Because partial derivatives commute. And there will be terms with first order partial derivatives of this, and they will actually also happen to cancel. It's impossible to see without writing it down, but they will also cancel. And I think there will be two more terms that cancel. And you will end up, and only four terms will survive. And they will include partial derivatives of Christoffels and Christoffels multiplying Christoffels. So a very complicated expression. And each one of those terms will multiply TK. And in the end, it'll be an expression like this. R, K, M, I, J, T, M. So that whole four terms, we will be able, obviously they have four indices. It'll have four indices. And we'll unite it by the single letter. And this letter is called the Riemann-Christoffel tensor. Riemann. These names that are pleasant to write down. Riemann-Christoffel It's not like writing Graham Schmidt and thinking, who are these guys? It's Riemann and Christoffel. Okay, the Riemann-Christoffel tensor. One of the most basic and fundamental and beautiful objects you'll ever find. But if you were to extend it in terms of Christoffel symbols, kind of messy, which is not a problem. It is what it is. Okay, so let's talk about this object, and let me convince you that this is identically zero, that we're looking at 27 zeros here. Question number one. So we're now assuming that T is a tensor. So question number one, is this a tensor? Yes, that's the whole point of developing the new derivative. Is this a tensor?
Yes.
Is this a tensor? Is this a tensor? Yeah, so this is a tensor. That's comforting to know, right? So we don't know what this is, but at the very least we know how it changes from one coordinate system to another. We know exactly how it changes. Well, let me call this S, K, I, J. Here's guys, I don't know what it equals, but here's how it changes from one coordinate system to another. S, I, J, K, J, I prime, I, J, J prime, J, J, of course backwards. J, K prime, K. The first two had to be reversed. I know that it changes according to this rule. It's a tensor. Okay, so we've built up all of that machinery to now be able to make these statements easily. Okay, great. It's a tensor. Let's see, can we think of one coordinate system in which we know what the value is? Let's try Cartesian or affine, but let's try Cartesian. What is this in Cartesian coordinate system? So let's think back to the covariant derivative in Cartesian or affine coordinate systems. What's the key property of the covariant derivative?
Partials.
It's just the same as partial, and so this is just be a partial derivative. And this is just the partial derivatives in the opposite order. So in Cartesian coordinates, these two terms are equal. So in Cartesian coordinates, this is 0. Now let's think of the unprime coordinates as the Cartesian coordinates. So in Cartesian coordinates, this is 0. All zeros, 27 zeros. So then in any other coordinate system, what is it? 0. Isn't that beautiful? All because it's a tensor. If we didn't have the tensor property, this argument goes out the window. But because it's a tensor, because it has this very special rule for transforming from one coordinate system to another, we can comfortably conclude that if it's 0 in one coordinate system, then it's 0 in all coordinate systems. It's one of the properties of tensors. I didn't want to mention it before without an application of that one rule. But if a tensor is 0 in one coordinate system, it's 0 in all coordinate systems.
Why is it 0?
Because in Cartesian coordinates, covariant derivatives are just partial derivatives.
Oh, S is the difference.
Yes, S is the difference, that's right. So the difference, so this difference is called a commutator. It is often written like this. I don't necessarily like this notation. Minus does this make sense, kind of? I don't like it. I don't like seeing operators without what they're applied to. But yeah, so it's the difference, and the difference vanishes in Cartesian coordinate systems, and therefore vanishes in all coordinate systems. So yes, conclusion. That's property. What are we up to? 7? Property 7, covariant derivatives commute. That's our final property. And it also implies that this object right here, that's not obvious. That this object right here is a tensor. So what we know is that this is a tensor. We know that this is a tensor. But not only is it a tensor, it's a tensor for any tensor T sub m. And there's a theorem called the quotient theorem. It's not hard, but I would suggest doing this in a couple of weeks where you're more comfortable with all of this. Prove that if you have any kind of product, any kind of contraction, which is a tensor of two things, A and B, and it's a tensor for any tensor B, then the object A is also a tensor. It's called the quotient theorem. It's very simple. In fact, I never remember its exact statement, and I just sort of prove these things over again whenever the situation comes up. Just use the same sort of argument. It's not hard to prove at all. Okay? So our conclusion is Riemann-Christoffel tensor vanishes identically in all coordinate systems because it's a tensor, and it vanishes in Cartesian coordinates for the reason we just mentioned, but also because it's some combination of Christoffels, and all Christoffels vanish in Cartesian coordinate systems, and because it is a tensor, it vanishes in all coordinate systems. So for tensor teachers, one of the favorite questions for their students, if a student comes and claims that they know tensor calculus, is to say, why don't you tell me the expression for the Riemann-Christoffel symbol in, let's say, in spherical coordinates? Right, and the expression for the Riemann-Christoffel tensor in spherical coordinates is 0. It's 81 zeros. If you go and start trying to figure it out, then you're, which is what I did when my father asked me this question, then you don't really understand it. Yes?
If it's always 0, why does it even exist as a
Oh,
symbol?
you're exactly right. Because when we repeat all of the same thing on a sphere, on a curved surface, where a Cartesian coordinate system is not possible, then this argument goes out the window, and this is not 0. And then it becomes a very interesting object. So we're preparing for our discussion of curved surfaces. That's answer number 1. Answer number 2, it's 0 in the Euclidean space where we have a position vector, we can differentiate it, get the covariant basis, metric tensor, and so forth. And also being in the Euclidean space, we assume that there's possibility of Cartesian coordinates or possibility of affine coordinates. But remember, it's something that I never mentioned in class when I brought the camera, but I did in our special sessions, that in Riemann spaces, it starts not with a position vector and God-given distance and ability to measure lengths and so forth, but with an arbitrarily assigned metric tensor. Metric tensor, which does not allow for Cartesian coordinates, just completely arbitrary. So you can imagine gravity warped the space. And I can take a tape measure and measure this board and get one value and then measure what I think is the same distance and get a different value. Because somehow space is warped, so the metric tensor is different at all points and just sort of arbitrarily assigned a priori before the discussion even starts. In spaces like that, the Riemann-Christoffel tensor won't vanish. It only vanishes if you're in a space where Cartesian coordinates are possible, which is not possible in a sphere and not possible in a general Riemann space, which Einstein says we'll live in. So that's why. And so when you hear that space is curved, someone's making the statement that the distances in our universe are such that if we were to measure the Riemann-Christoffel tensor, it won't vanish. Cool. All right, that's it.